Okay, when you take a look at your part, so each part number or each datasheet, it comes with part number and supplier or your manufacturer. So this is produced by ON Semiconductor. So maybe it represent the same part number, but the component body shape or body package might be the different, comes in different packaging. So you can see here, it does not have any holes to attach your heatsink in your part into heatsink. So what you have to do is that you either solder it directly into your heatsink, into your board here, this one, into your board, or you can click to the heatsink and click to the heatsink. You cannot screw. So either one. So if you click, you shall have at the back of this part, you have to put solder heat paste, thermal paste. If you solder directly to the board or the PCB, so the connection will be directly contact or firmly contact with the PCB board. That's why when we consider our thermal resistance value, you can see here, for MOSFET, just now we consider MOSFET, our thermal JC, we just found that this is from table, the value is 2.65. But in terms of our thermal CS, this part should be obtained from our what so called manufacturer of thermal paste or the thermal insulator. But when we just directly solder to the board or PCB, so that's why we have here zero resistance, means that the connection is firmly contact with the board. Okay, that's why zero resistance. Meanwhile, thermal JA is the value that we just mentioned just now. If we don't use any of our heatsink, so this will be the value 2.65 and 65. Okay, so this is how you read your data inside your data sheet. Okay, so come back to here. So 2.65 because we are going to use the heatsink, so plus TC. Now we have to take a look at how much is our PD now. So PD is equal to I square RDS during switch on. So we have here two losses actually for converter, which is conduction loss and switching loss. So for the time being, we are considering the conduction loss, RDS on. So RDS on at value of 100 degrees C. So we put here I square RDS on at 100 degrees C. Okay, RDS on at the value of just now, how much? We're looking at 100 degrees C. So if we take a look at our data sheet, so we have here RDS on, even though in the front page we have here 165 milliohm, RDS on 165 milliohm. Or you can see directly inside your on characteristic of this device, how much from drain to source their on resistance, which is stated over here. Typical value of 0.13 or maximum value of 165. So as I told you before, we can use this 165, 0.165 as initial calculation, such that when we have certain issues of to accept or buy off certain parts inside our production line, we still have allowable what's so called tolerance, because the typical value is smaller. Okay, but if you take these values as our initial consideration, means that if the part is not passing in the line or production, so we have to put or reject. See, this is the issue of reject or accept when you work inside production line in your factory or whatever lah. So if we take the maximum limit, so we can squeeze some more in terms of design spec or allowable design criteria later. If we take this value, so it's no more can be squeezed. No? So let's say we follow the example inside the notes. So just we use this typical, okay? Use typical, but okay, 0.13. 0.13 means that we have here 0.13. This is the another value which is indicate at certain values of junction temperature, but this is the value of initial condition at 25 degrees C. See here. Later at another values of temperature, we shall use their normalized factor to multiply how many ratio to get the values of at that range of temperature. So this is your RDS on value at 25 degrees C. What happens if the temperature that we operate is not at 25 degrees C? So you can see this from this figure 5 here. On the system variation with temperature means that if it operates at 25 degrees C, so it will follow the ratio of 1. So 1 times 0.13, so means that remain as 0.13 ohms. But if you operate your temperature of your junction at 50, 75, maximum up to 175, so you have to multiply by this factor. So this is your normalized factor. Means that if you operate at 175, so you have to multiply 2.5 times 0.13. Now if you want to operate at 100 degrees C, so we take a look here, so about around 1.6 something times 0.13. That's why when you take a look at your table here inside your notes, so we have here RDS on at 25 degrees C is 0.13, but here we have 0.14 because I'm not sure, maybe this one refer to another manufacturer, but for our manufacturer now, just now is 0.13. So let's say if it is 0.14, so this happen at 25 degrees C. If you operate or we shall maintain your junction temperature at different values such as 50, 75, 100, 125, so this is your multiplication factor, and so you have to multiply by this value. That's why means that 25 degrees C, so the initial value times 1, so you get this one as your RDS on MOSFET, and PD MOSFET means that your current here multiply by 2 times RDS on, you get this value. So this is how you get your RDS on value. This value 1 times 0.14 is 0.14. 1.2 times 0.14 you akan dapat 0.168. This one multiplication of 1.875 times 0.14 you akan dapat 0.2625. Means that you get this from your curve, calculate with this RDS on normalized factor, you akan dapat this value. Okay, so this is how you determine RDS on multiply initial value times the normalized factor. So you write here, but RDS on 100 is equal to 0.14 from the curve times how much the factor. So it is just about what so called projection. You might not get up to this actual values of 0.625 like that, and maybe you can write as 1.6 or 1.63. So this sufficient because we are just projecting. So 0.1 is 1. So times 1.3 like that. Okay, so this is your RDS on value, which is just now mentioned as how much? 0.23. 0.23. This is your RDS on value. 0.234. So in calculation you don't need to put units, but at the end of your result please put your unit. Okay, then we settle with other one. Then we have to find how much is our I. Yeah. So this I is IRMS. So IRMS. So even though you might not have to calculate, so we just discuss how actually the values is obtained. So first we have to find actually how much actually the average voltage that being induced to our system just now. So we can see that the MOSFET is operating at 0.6 or 60% on. Another 40% it will flow into our rectifier. So the average MOSFET voltage will be duty cycle times the total total voltage applied to the system. 0.6 times 100 means that average voltage will be induced at 60 volts. And so V average divided by R, you get 6 ampere of average. 6 ampere of average current. And your RMS current will be for your MOSFET. MOSFET will be IRMS will be third of MOSFET duty cycle times average current. So we have here 0.6 times 6 volt ampere just now. So this is the values of your current RMS that passing through your MOSFET. 4.65 ampere. So 4.65 ampere. 4.65 is your IRMS. So IRMS equal to 4.65 ampere. So 4.65. So your PD will become I square RD S on at 100 AC, which is 4.65 square times RDS on, which is just now 0.23 ohm, 0.23. So you akan dapat di sini, so dapat 4.92 watts. So this is your dissipated power which produced at TG, and TG of your MOSFET. So this is the TG punya MOSFET dissipated power which generate at the MOSFET. Then return back to here, and the value of PD just now, you put it back in here. So you shall get your TG, which is equal to PD R thermal JC plus TC, which is 100 times 4.92. So 4.92 plus R thermal JC, which is just now 2.65. 2.65 plus TC. So now we are able to find the unknown of TC, which is how much? Which is 6.96 degrees C. So what we are doing right now is we are calculating all the components which is not available here. We have this value, we just put it there. We have this value, all this value. So this one already just now we got as 0. So this one also 0. So TS and TC are the same because this is 0. So this is what we calculate now, and the value of our TC. And the unknown is going to be calculated, or to be find out how much. So means that all the components that we have, we put a label here, need to be calculated and put in place, and how much all of these values. So that is the aim of our task